Good morning, good afternoon, good evening from wherever you're listening from in the world. This is Brendan Slade from the LPC product line team in NXP. And with me today is Andy Ebb from Embedded Systems Academy. And they're one of our key partners who help out with CAN and CAN-FD solutions for the LPC product family. And today, Andy's going to be doing the bulk of the presenting, talking about CAN and CAN-FD and how they compare to each other. So Andy's going to be doing controlling of the presenting here, so I'm going to be asking to press the buttons. So if you could do the honors there, Andy, we'll move on to the agenda slide. So I'm going to start with a quick introduction of the LPC family as it relates to CAN and CAN-FD, but we'll quickly move on to the meat of the presentation, which is what Andy's going to be talking about. So we'll introduce Embedded Systems Academy, who they are and what their specialist skills are. Andy will then be moving on to comparing CAN and CAN-FD and how they differ. We'll dig a little deeper into the CAN-FD protocol and look at how that's implemented on the LPC5461x family, which is one of the more recent products from NXP. The CAN controller block diagram will glean some useful information about how the whole system works. And after Andy's been through those details, he's going to talk a little bit about how CAN-FD can help in various applications. We'll then look at the support available for those of you who need a little extra help to do your CAN-FD implementation, and where you can get a CAN open. See the last technical part in the software drivers that ESA have developed for us for the LPC family, and that will include a demonstration by Andy. So if we can move on to the next slide, Andy, I'll introduce the LPC family. So for those of you who don't know, LPC has been around for a long time, starting from ARM 7 and 9 products and then moving into Cortex-M products. And our customers stay with us for a number of reasons. And we have over 10,000 active end customers on LPC. And this product family that we have is underpinned by a broad ecosystem, but that includes some very key specialists like ESA, who really add a lot of value to our customers and help implement these kind of solutions. LPC micros are used in a whole range of different applications, from industrial, medical, consumer, and so on. So in all those different kinds of applications, in many cases you need a very long life and high quality, and LPC offers those things along with other products in the NXP portfolio. And our distributors help provide worldwide support for our technology. So on the next slide, I talk about the LPC family. So CAN has been part of our product portfolio for quite some time. In this diagram of our product family, the product boxes with the red markings around the outside are those that have different members of the family with CAN capability. So this starts down at our LPC 1100 family with the 11C products. These are Cortex M0 based. Then we get to the M3 range of products, and so we have a range of different parts that have CAN capability there, and some of those are dual CAN solutions. And then into the higher end performance, where all of our families have some representation with the CAN feature. And most recently, the LPC5461x family within the 54000 series includes CAN-FD options as well. So on the next slide, we have a look at the 54600 block diagram, and the CAN-FD block is dotted there. So there are parts with just classic CAN and then other options with CAN-FD. The 5461x parts have the CAN-FD option. So you can see that this product has a wide range of peripherals, so it's a very flexible device, good amount of flash and RAM, and a very good low power capabilities. And most recently we released 100-pin packages versions of these parts for more cost-effective CAN-enabled solutions. The products are not automotive grade, but can be used in aftermarket automotive because they have the temperature range to match that requirement. And they have a wide range of operating voltage too. The operating frequency of the CPU goes up to 180 megahertz. We have plans to push that a little further, so watch announcements from us over the next month or so, and you'll see what's coming there. Okay, on to the next slide. The board that Andy's going to be using today is the standard CAN-FD development kit for the LPC5461x rather. And so this is a very flexible board. It has lots of memory, courtesy of Micron. We have a microphone from Knowles in there as well, not listed here. We have lots of peripheral connectivity, Ethernet, digital mics and SD cards, USB, and so on. So in the case of CAN-FD, those connections to serial ports, USB, obviously quite often are very important. This kit features a shield board which plugs on. It's a kind of an extension to the Arduino connection standard, and it plugs on the back of the board there, and it gives you a dual transceiver, which is another NXP product, the TJA 1059, and it also has a serial port on it too. So this board is fully supported by the MCU Expresso SDK and with MCU Expresso IDE Kyle and IAR tools, and the drivers that Andy has developed for us, or ESA have developed for us, are available on the NXP website. So on to the next slide. Now I'm going to hand you over to Andy. He's going to take it from here and start with an introduction to Embedded Systems Academy. Over to you, Andy.
Thank you, Brendan, and welcome to this webinar. Embedded Systems Academy provides a range of services related to embedded systems with a focus on the CAN bus. We provide consulting services, including development of custom firmware and PC applications, and we offer on-site CAN-related training courses, which can be combined with consulting to jumpstart new projects. Our main focus is CAN, and CAN Open in particular, which is a higher layer protocol for CAN. And we have a range of embedded stacks, PC tools, bootloaders, all related to CAN Open. We also do a little bit of work with J1939. We have a stack for that, and some people may be familiar with us from FlashMagic, which is the ISP tool for NXP Microcontrollers.
Andy, sorry to just jump in there, but we do have a questions box. If people attending would like to type in their questions, we will try and address those at the end if we have enough time. Thank you.
Okay. So our first section is to look at what benefits CAN-FD can give us and why we might want to use it over regular CAN. Throughout this webinar, we'll use the term classical CAN to refer to the previous implementation, which is up to 8 bytes of data on 1 megabit per second, and has been around for quite some time, so hopefully you're somewhat familiar with that version. So CAN has been around since the late 1980s and has proved itself to be a robust and popular networking choice for a wide range of industrial and automotive applications. In 2011, Bosch came up with an improvement called Flexible Data, or FD for short. This new protocol went through some early revisions before committing to silicon around 2014. During the ISO standardization process, some flaws were discovered related to error detection, and these flaws were corrected, and CAN-FD became an ISO standard in 2015. This means that there are 2 versions of CAN-FD, the old version and the ISO standardized version. It's possible to use the old version with the LPC5461x, but it's not recommended for new designs or production going forwards. You should only use the ISO version, is the only one to use really. There are 2 key differences between classical CAN and CAN-FD. The first is that much higher bit rates can now be used. So classical CAN is limited to 1 megabit per second. CAN-FD doesn't have a theoretical limit, but in practice it is limited by the transceivers. Currently transceivers available that are rated up to 2 megabits per second, and we've been able to achieve speeds of 4 megabits per second with those transceivers. That's already a significant performance increase while retaining the qualities of CAN that make it popular, such as the error detection and reliability. And it's expected that transceivers supporting higher speeds will become available. The second key difference with CAN-FD is the increased amount of data per CAN message. So classical CAN is limited to 8 bytes, and this can be a challenge for some applications to deal with. For example, in the higher layer protocol CAN Open, there are 2 approaches commonly adopted. There is a software protocol that handles fragmenting blocks of data over multiple messages, and there is a desire to try and keep data objects less than 8 bytes in size in these protocols to avoid having the hassle of fragmentation handling. With CAN-FD, the limit is increased 8-fold to 64 bytes per message. So the result is much less need for data fragmentation in typical networks. Taking into account the additional bits in the control field of each FD frame, the resultant throughput can be up to 6 times higher than classical CAN. CAN-FD controllers can be configured to use only classical CAN mode, and providing all CAN-FD controllers are configured this way, then the network can use a mix of CAN-FD and non-FD controllers. However, if a CAN-FD controller is configured to only use classical CAN, then it will treat any received FD frames as error frames and destroy them. So there is a level of backwards compatibility, and it gives a migration path for legacy software. If a single CAN-FD controller is configured to transmit FD frames, then all CAN controllers on the network have to be CAN-FD controllers. Otherwise, as I just mentioned, they have a lot of error frames. To go beyond the maximum classical CAN speed of 1 megabit per second, the transceivers used must be compliant to the CAN-FD standard, which means they have to be able to handle the higher bit rates possible. So classical CAN supports the concept of remote transmission requests, or RTRs for short. This is a mechanism whereby a node can request another node to send a specific CAN message containing data. Unfortunately, implementation of this feature in CAN controllers was not consistent over the years, and its use generally was not recommended. So with CAN-FD, this feature has been completely removed. A bit has been added to the CAN frames to indicate the error status of the CAN controller transmitting the frame. This allows all nodes on the network to see if there's a problem or a potential problem with another node. This bit is accessible to the software layer, allowing firmware to be designed to detect and take action when the situation arises. Classical CAN has a weakness that was discovered after it was already in widespread use, so too late to change, and it was allowed in specific situations 2-bit flips in the data to occur without being detected, despite the use of a CRC checksum in each frame. So CAN-FD solves this weakness by changing the way the CRC and special bits in the frame are used to detect errors. With CAN-FD, it now requires 6-bit flips to occur before errors cannot be detected, leading to an increase in robustness and reliability. At the lowest level, the wiring used, which is typically twisted pair, and the topology can remain the same. For higher bit rates, the topology of the network may need to be adjusted, for example, shortening cable lengths and changing termination values. However, the physical layer remains familiar to current CAN users. This means that CAN-FD networking has the same infrastructure costs as regular CAN. The second section of this webinar looks at how CAN-FD appears on the lowest level. CAN-FD frames have a familiar format to CAN users. The frames start with an arbitration field which governs bus access by message priority. That is followed by the control field, which defines a type of frame. Next is the data, which can now be stretched to 64 bytes. The CRC checksum is after the data, followed by the acknowledge, end of frame, and intermission field. So it's very, very familiar to anybody who's worked with regular CAN. The arbitration field governs access to the bus. As it's primarily based on the message identifier, it means that lower identifiers will always win arbitration, same as classical CAN. The arbitration field is identical to regular CAN. The RTR bit has been renamed to RRS, which stands for Remote Request Substitute, and basically is a reserved bit. When the frame is an FD frame, the SRR and RS bits are reserved. RS is always transmitted as a dominant, which is logic 1, and may be renamed in some documentation to R1. You may see it as R1. SRR is always transmitted as recessive. The top diagram is for the control field for 11-bit identifier frames, and the bottom diagram is for 29-bit identifier frames. The control field has been changed from classical CAN to accommodate the new CAN-FD functionality. The first previously reserved bit is now used to indicate if the frame is an FD frame, and that bit is called FDF. 2 new bits have been added. BRS enables the bitrate switching, which I'll describe in a moment, and ESI indicates the error state of the transmitting node, whether it's error active or error passive. The data length encoding remains the same at 4 bits. The values 0 to 8 are used to indicate the number of data bytes, which is the same as classical CAN. In order to support up to 64 bytes of data, a different encoding is used. This means that only specific lengths of data are supported beyond 8 bytes. The table shows the possibilities. So, for example, you cannot have 35 bytes or 49 bytes. It has to be one of these lengths. The checksum field now starts with an encoding of the number of stuff bits that have been inserted into the frame up to that point. The stuff bits are inserted automatically after a sequence of bits with the same state in order to create periodic edges in the waveform for synchronization between the CAN controllers. The stuff bit count solves the previously mentioned checksum weakness. A parity bit is used to protect the stuff bit count itself from undetected corruption. The CRC field size depends on the number of data bytes in the frame. So, for example, messages up to 16 bytes in length, the CRC looks as shown in the diagram with 17 bits. Frames that have more than 16 data bytes use a 21-bit CRC. With CANFD, the CRC field always has stuff bits inserted every 4 bits to ensure CANFD doesn't have the same checksum weakness as the previous version of CAN. Note that classical CAN frames transmitted by a CANFD controller use the old checksum field format, providing backwards compatibility. CANFD controllers support transmission and reception of FD and non-FD frames at the same time. Providing all transceivers are FD compliant and all CAN controllers are also FD compliant, the 2 types of frame can appear on the same network. The FDF bit selects the FD frame format. Both types of frames support 11-bit and 29-bit identifiers. The FD frame can be transmitted with all bits at the same speed, or the data bits can be transmitted at a higher speed. This optional feature is selected through the use of a bit in the frame called the bitrate switch, or BRS for short. When bitrate switching is enabled, the start of the frame containing the message identifier is transmitted at a lower speed called the nominal bitrate. This is the same speed that classical frames are transmitted at. When transmission of the first data byte is about to begin, the bit rate is automatically increased to the higher data bit rate. The checksum is also transmitted at the higher speed. At the end of the checksum, the speed is lowered back down again to the nominal bit rate for the final few protocol bits of the frame. Switching of the bit rate is handled automatically in the CAN controller, and all of this is transparent to the software layer. The data bit rate cannot be lower than the nominal bit rate, but it can be the same. And note that error frames are always transmitted at the nominal bit rate. Here we have a scope waveform, and at the top of the image showing a bit rate switching. It can clearly be seen that the data phase in this waveform is significantly faster than the arbitration phase. So this particular example, the arbitration phase is at 1 megabit per second, and the data phase is at 12 megabits per second, and there was 64 bytes of data in this message. The length of the network was 42 meters, and the transceiver used was an NXP TGA1040. Note that the TGA1040 is rated up to 1 megabit per second, but as you can see, it can be made to work for higher speeds. This table shows all the possible combinations of frame types that can appear on the bus. Note that RTRs are excluded from this table for clarity, as they're not typically used. Whereas for regular CAN, there are only 2 different frame types. CANFD now has 6. For transmission, the FD and BRS bits can be set on a per message basis. And with receiving frames, the FD and BRS bits are made available to allow the software layer to be able to tell how a frame was transmitted. But that is not commonly needed by the software layer, as the exact method of transfer can be regarded as transparent. Just like regular CAN, it's possible to configure the sample point. This is the precise timing inside a bit period where the CAN controller samples the state of the bus. This point is configurable to take into account the speed and topology of the bus. With CANFD, it is now possible to have 2 bit rates inside a frame. Therefore, it is also now possible to have different sample points for the different bit rates. This allows the ideal configuration to be used for the specific network being designed. However, all CAN controllers should have the same configured for the same sample point. All CAN controllers have two error states, active and passive. In error active, the controller is fully participating in communications on the bus, and in error passive, the controller cannot transmit error frames. A controller enters error passive mode due to errors transmitting and typically indicates a faulty configuration or hardware problem. CANFD allows the current error state of the controller, active or passive, to be indicated in a CAN frame using the new ESI bit. This allows all of the nodes on the bus to determine when a controller is in the error passive state and may have a problem. Action then can be taken in the software layer, for example, attempting to reset the node, setting its own outputs to a default state. Stuff bits are inserted at the hardware level of the transmitter to ensure there are frequent synchronization edges inside CAN frames. These stuff bits are removed at the hardware level of the receiver. CANFD frames have an encoding of the number of stuff bits and employ fixed stuff bits inside the checksum field. Both these aspects improve the detection of errors in FD frames. Previously, 2 or more flipped bits could be undetected with classical CAN. Now, undetected errors require at least 6 flipped bits in an FD frame. So we will now look at the CAN features on the NXP LPC5461x. The LPC5461x features 2 identical CAN controllers. Both CAN controllers conform to the ISO standard and support CANFD. For the rest of this section, I'll discuss a single CAN controller, but all my comments apply to both CAN controllers on the part. It's possible to enable and disable FD functionality and bitrate switching at the global level in the control register. When disabled, the controller will operate in classical CAN mode only. It will not be possible to transmit FD frames. Any FD frames will be treated as error frames and destroyed. So this is useful for applications that are migrating from other microcontrollers and currently don't need FD functionality. And the default configuration is for this functionality to be disabled. The CAN controller requires the use of regular SRAM to operate, and the SRAM is used for describing filters and storing message buffers, and also for the FIFOs. The controller has a highly flexible approach which allows the use of anywhere in SRAM. A base address is specified and then offsets are used to the start of the various RAM sections. An interesting aspect of this RAM arrangement is that the RAM used by each of the CAN controllers can be overlapped, making bridging applications very easy to implement and minimize the shuffling around of data. As the diagram shows, there are 7 sections that can be located in RAM. If a section isn't required, for example global filtering, then it does not have to be used. And each section has its own 16-bit RAM address offset from the 32-bit base address. This means the order of the sections can be customized and they don't have to be contiguous. So there's a high degree of flexibility with the RAM allocation. Two separate receive FIFOs are available. Each FIFO can be configured in blocking or non-blocking modes. Non-blocking acts like a circular buffer, and blocking mode stops receiving when full. FIFOs can be configured in size from 1 to 64 messages, and each FIFO can also be disabled. Interrupts can be generated when a certain number of messages are in the FIFO and also when the FIFO is full. In addition to the FIFOs, there are 64 receive buffers available. Each buffer can receive a single CAN frame and generate an interrupt on reception. FIFOs would typically be used for processing received messages in order, and messenger buffers would typically be used for giving priority to specific messages. The most common arrangement with CAN controllers is to directly associate the message filtering and message buffers. A particular buffer has its own filtering configuration usually. With the LPC5461x, the filtering is separated from the message buffers and the FIFOs. This allows multiple filters to be defined and associated with a single message buffer or FIFO, allowing complex filtering schemes to be constructed, and this is ideal for high-layer protocols. For simple applications, the complexity of message filtering can be avoided by allowing all messages to be received and then handled in the software layer. It's also possible to define rejection filters. If a message matches the filter, it is rejected. This is useful for situations where a node needs to receive majority of the messages but perhaps some frequently transmitted messages are not useful or required and can be blocked from being received. Received messages can be timestamped at moment of reception with configurable timestamp precision. The timestamp counter is a free-running 16-bit counter clocked from the same clock that is used to generate the CAN bit rates. The counter has an 11-bit prescaler, allowing the resolution of the timestamps to be configured. Received message filters can optionally be configured to designate a message as high priority. When received, a separate interrupt occurs, and a status register allows the software later to determine which FIFO or message buffer holds the high priority message. 32 transmit buffers are provided. Some of these buffers can be allocated to a transmit FIFO or a transmit queue. It's possible to have 32 transmit buffers and no FIFO or queue, or you can have no transmit buffers and a FIFO or queue with 32 messages, or anywhere in between. So you can take the 32 message buffers and decide how much is dedicated and how much is in a FIFO or a queue. By combining a queue or FIFO with dedicated transmit buffers, it's possible to transmit messages in order by putting them into the queue or FIFO, but also prioritize transmission of other messages by putting them into a dedicated transmit buffer. For example, if the oldest message in the queue or FIFO has identifier 200, and a message with identifier 100 is put into a dedicated transmit buffer, then that message will go out first, effectively jumping the queue or FIFO. The FIFO acts like a circular buffer and transmits the messages in the same order that they were inserted into the FIFO. When configured as a queue, the controller always transmits the message in the queue with the lowest identifier, so the transmission order may be different to the order the messages were inserted. Every time a message is transmitted, a transmission event can be stored in a separate FIFO. This allows the software layer to determine the transmission order of messages and obtain a timestamp of when the message went out onto the bus. The timestamps are generated from the same timestamp counter that is used for received timestamps, therefore allowing the relationship of transmitted and received messages to be determined. The size of the event FIFO is configurable from 1 to 32 messages and has its own fill level interrupt. Each CAN controller has 2 interrupts, 0 and 1. Any interrupt source can be allocated to one of these 2 interrupts. This allows division of code between the 2 interrupt handlers. For example, one could be dedicated to receive and the other one could be used for everything else. Higher layer protocols are supported. In particular, the needs of AutoSAR are accommodated, which requires transmit cancellation. The highly flexible filtering is well suited to CANopen and J1939. Various test modes are available, including loopback, which can be used for power on self-test, along with directly monitoring and driving the transmit-receive pins if required. A restricted operation mode is provided. This allows a controller to receive data and acknowledge frames, but it cannot transmit and does not generate error frames. This is ideal for implementing autoboarding, where the CAN bit rate needs to be automatically detected without disrupting the network. Various bit timing configurations can be tried until a working one is found, and then restricted operation mode is exited and full communication is possible. A power down mode is supported, and any pending transmit requests are completed first. Internally, the clocks are turned off inside the controller. All CAN controllers work by being able to detect if what they're transmitting onto the bus is what is actually appearing on the bus. A controller does this by comparing the state of the transmit pin with the state of the receive pin, and this is used, for example, in arbitration. With the ability to transmit data at a much higher rate than before, this creates a potential issue. If the delay for the signal to go from the transmit pin through the transceiver and back to the receive pin is longer than the time from the start of the bit to the sample point within the bit, then the transmitter will detect a bit error. The solution is to enable transmitter delay compensation, which creates a secondary sample point inside the bit only used by the transmitter. This is enabled by setting a bit in the data bit rate register, and a compensation value can be specified. We'll now look at the block diagram of the on-chip CAN controller. A CAN controller consists of a CAN core, control registers, a HB interface, and message handlers. The CAN core is the CAN protocol controller and the transfer and receive shift register, and it handles all the protocol functions. The transmit handler transmits messages from the RAM to the CAN core, as well as providing status information. The receive handler manages acceptance filtering and transfers received messages from the CAN card to the RAM, as well as providing status information. Interrupts and timestamp block handles interrupt signal generation and timestamping of transmitted and received messages. So we'll now look at the typical applications that can benefit from the new features of CAN-FD. The improved error detection characteristics suit applications in safety-related sectors such as automobile and medical. The ability to transfer 64 bytes per frame is ideally suited to firmware updates, allowing such updates to be performed far more quickly with less downtime and perhaps without even taking the network out of commission. Applications which require the periodic update of displayed data will be able to take advantage of the larger frame sizes. For example, transferring HTML or process data becomes more convenient with less message fragmentation required. CAN-FD allows for more security schemes to be implemented. The additional frame size and speed means that a portion of each frame could be dedicated to encryption or authorization without reducing existing throughput. More specific to the LPC5461x is the ability to generate precise timestamps for transmit and receive from a single time source. This allows data loggers to be developed with the ability to obtain detailed timing information. The next section briefly covers support options for CAN-FD. Support for all aspects of using and developing with CAN and CAN-FD is available from us. We have many years' experience with technology and familiarity with the problems typically encountered. We offer consulting and troubleshooting services, both remote and on-site, as well as complete firmware development. We will also be providing support on the NXP forums for issues that relate to microcontrollers. The CAN in Automation is the standards body that governs CAN-Open, and they're currently in the process of working on adapting CAN-Open to CAN-FD, and once they do, we will have a range of embedded stacks and development tools to suit. So I will now cover the API that has been developed for this microcontroller family to ease software development. The API is based on the FlexCAN API for the Kinetis K60. So if an engineer has used that before, then hopefully the migration path will be smooth and painless. Some changes were made to accommodate the differences in the CAN controllers, and most of the changes relate to how the message filtering is configured. The provided examples demonstrate sending and receiving of CAN-FD frames with up to 64 bytes of data and up to 4 megabits per second data speed. Examples for MCU Expressor and Cal Microvision are provided. The setup consists of an LPC5461x evaluation board and CAN shield, as Brendan already outlined. The shield provides the CAN transceivers and 2 D-type connectors for both CAN controllers, which makes connecting to standard CAN cabling very simple. We have a pecan USB, FD, CAN interface and standard terminated cable. The configuration is fairly straightforward. There is a function in the board support library to set up the pins for use with CAN. In this example, we use both CAN controllers and to configure the pins for both of them. Initialization is performed by calling init and passing a structure with the settings to be used. The API provides a function that can fill in the structure with reasonable defaults, so only the differences need to be explicitly configured. And once initialized, an enable function is called to enable the CAN controller. So pretty straightforward. The structure that defines the CAN controller configuration has various fields. A nominal baud rate sets the nominal speed in bits per second, and if you recall, that's the speed for arbitration. Data baud rate sets the data speed in bits per second. If this value is 0, then bitrate switching is disabled, and all frames are transmitted at the nominal rate. The base address is a 32-bit address in SRAM, where the API will store filters, buffers, and FIFOs. The SRAM usage is contiguous and the amount used depends on the number of buffers and FIFOs used. Timestamp clock hertz is the desired speed of the clock in hertz that generates the transmit and receive timestamps. A value of 0 disables timestamping if it's not required. The possible range of values is limited by the clock configuration used for the CAN controller. Reject standard RTR, reject extend RTR, Boolean settings to specify whether remote transmit requests will be accepted, and this is for classical CAN mode. Enable loopback is a Boolean setting to enable or disable loopback mode, used for testing. Enable non-ISO mode, when true, uses the version of CAN-FD that was before ISO standardization took place, and in general recommend this should always be false. Disable FD, when true, configures the CAN controller for classical CAN mode with no FD support, so that's for backwards compatibility. Note that for this to work, we need to know the speed of the clock to the CAN controller. This is easily achieved by calling the standard function, system core clock update, and then using the system core clock variable. These set of functions configure how and what can be received. Use of the FIFOs is optional, and if either of the FIFOs are to be used, then set RX FIFO config is called. This sets the size of a specific FIFO and enables it. The CAN controller supports a simplified global filtering arrangement, which is optional. If desired, calling set RX global mask can configure all 11-bit and/or all 29-bit messages to be automatically accepted and placed into a FIFO. So if you want to do all the handling, receive handling in software, this is the easy way of configuring the receive of the CAN controller. For fine-grained control, set RX individual mask can be called. This enables filtering for 11-bit messages. Each call configures a specific message filter, and the results of passing a message through that filter can be stored either in a FIFO or in a dedicated message buffer. The destination for the filtered message is determined by using the appropriate macro when calling the function. On the slide you can see the 3 macros listed, and each macro takes a message identifier and a mask. This function is the same as the filter function which is discussed, except this is for 29-bit messages. There is a separate set of macros for these, and each function call requires 2 macros, one for the lower 32-bit part of the filter and one for the upper 32-bit part of the filter. Messages can be transmitted by placing them to specific message buffers, or they can be transmitted using a FIFO or a queue. A mixture of buffers and FIFO or a queue can be used. In order to transmit using a message buffer, then the buffer has to first be enabled, which is achieved by calling set txmb config. There is no configuration required to transmit using the FIFO or queue. The size of the FIFO or queue must be set using the pound defines, but once configured, it's available for use. Non-blocking transmission is supported, and this allows a message to be passed to the driver and then later on to receive notification that it was transmitted. Before using non-blocking transfers in any direction, a handle has to be obtained from the API. This handle simply associates a specific CAN controller with a callback function, and there's only one handle per CAN controller. Transfer send blocking transmits a message and doesn't return until the message has appeared on the bus. Passed to this function is a structure that defines the message. Length holds the message length in bytes. Type specifies if the message is an RTR or not for classical CAN. Format defines if the message is an 11-bit or 29-bit identifier. Proto is used to enable FD frame transmission for this message. If it is set to false, then the message is a classical frame with a limit of 8 bytes of data. Bitrate mode enables bitrate switching. ID and data word and data byte specifies the message identifier and the length. Note that the same message structure is used for receive as well as transmit, so you can easily echo messages. Transfer send non-blocking is called to request a message is transmitted. This function returns immediately. Once transmission is completed, the callback function is called with the status. It's important to note that the message buffer cannot be reused until the transmit is completed. In order to use this function, a transfer create handle must first be called to obtain a non-blocking transfer handle. It's possible to abort a pending transmit by calling transfer abort send. Calling write txFIFO to transmit using transmits using the FIFO or a queue, and passed is the messages transmit, which is then placed into the FIFO or queue, and the function returns immediately. Transmission will then occur according to the rules of the CAN controller. The function will turn a failure code if the FIFO or the queue is full. Read RX FIFO and read RX MB provide a way to pull for received messages. Calling either function will return any message waiting to be read, and in the case of the FIFO, the oldest message waiting to be read. Just like we saw with transmit, non-blocking receive is possible. Transfer create handle is again used to obtain a handle, so the same handle is used for both transmit and receive. When transfer receive non-blocking is called, it sets up the driver to look for a message to be received into a specific message buffer. This continues until either the message is received or transfer abort receive is called. And on reception, the callback function is called. There are two matching functions to achieve the same non-blocking operation, but with the FIFOs instead of the message buffers. Dinit can be called if the CAN controller is no longer needed, and this will completely switch off the controller. GetBus error count gets the current values of the error counters, which is sometimes useful for the application layer to know this. Get status flags get the current status flags, allowing the application layer to respond to bus off error active, for example. I'll now give a short demonstration of using the API. This demonstration doesn't cover all functionality, as some of it is mutually exclusive, but it will demonstrate configuration, transmitting and receiving. For the demonstration, I will switch over to the MCU Expresso IDE. In conjunction with this, I'm using an application called pCAN View. This is a free utility. It comes with all pCAN interfaces and allows straightforward, simple transmitting and receiving of messages. So I want to begin by describing the setup we are using. Here is a camera view of the board and the CAN controller. So we have an LPC Expresso board with an LPC5461x, and connected to the board is a CAN shield which provides the transceivers and connectors for both the CAN controllers. Alongside that, I have a USB CAN interface, and the interface is connected to both the CAN controllers. So we have a total of 3 devices on the bus. We have the CAN interface from PEAK, and we have the 2 CAN controllers on the microcontroller. At the bottom, I have pCAN View running. Currently, there's nothing showing in the window. And at top, we have MCU Expresso running, and we're currently debugging an example application that I'll go through. So this example demonstrates transmitting and receiving messages using the FIFO. Received messages are handled in a callback function, which in the API is the equivalent of a CAN interrupt handler. The first few lines of main update the system core clock variable, initialize the board support, and set up the CAN controller pins. So pretty straightforward. At this line here, we are getting the default configuration and then changing just the settings that we want to use. For example, we're setting the base RAM address and the bit rates, which are 1 megabits per second for nominal and 4 megabits per second for data. We also specify the timestamp clock speed of 100 kilohertz. Then we call the init function, passing the configuration. So the point to take away from this is that you don't need to worry at this level on how to work out the timing, the registers to configure the timing for the CAN controller. The driver handles this for you. It takes the data baud rate, it takes the nominal baud rate, and it works out a clock configuration solution that suits both. Here we configure receive FIFO for CAN 1. We're setting the size of the FIFO to 64 messages. Pretty straightforward. Next, we setting a global mask saying that we want to receive all 11-bit and all 29-bit messages into the first FIFO for CAN 1. Next we create transfer handles because we want to use a non-blocking send and receive. We only need to do this once for each CAN controller, and it's just, as I mentioned before, it's a way of associating a callback function with a particular CAN controller. So we pass a function pointer for the callback function, and we get back a handle that we can then use to tell inside the callback function which CAN controller has called it. Now, calling this doesn't actually configure anything for non-blocking transfer. It just makes it possible for us to use those set of functions. Next, we enable the CAN controller, enable both of them. Here we specified that the next message that matches the filtering for the receive FIFO, we want it to be non-blocking. So we want the callback function to be called whenever a message is received on CAN 1. And we pass the buffer here, Rx message, which is where the received message is going to be accessible through after it's been stored in the FIFO. We've got configuration for system tick handler and for the LEDs. Here we have the while loop, and all we're doing here is periodically transmitting messages, and for these messages we're cycling through message identifiers 100 to 102 for a bit of variety. It's pretty straightforward. We're initializing a message structure and then calling can write tx FIFO to transmit it using the transmit FIFO. We're using 11-bit identifiers. We're using an FD frame with bitrate switching, and we're sending 64 bytes of data for this particular message. So if I start execution, we should see the messages being transmitted in PCAM view below. So here we can see every 300 milliseconds we're getting our 3 messages being transmitted with 64 bytes of data, and here is the data. And all 3 of these messages have the FD flag and the BRS flag set. So they're using FD frame format, which allows us to send 64 bytes, and baud rate switching is turned on, so the data is being transmitted at 4 megabits per second. If we now take a look at the callback function briefly, when this is called, we receive a handle, and the handle we previously obtained allows us to tell which of the 2 CAN controllers called this function. You could also have 2 different callback functions, one for each CAN controller. Passed is a status value. Here, Rx FIFO idle means that the receive FIFO has just finished storing a message. We're then able to extract that message from the FIFO, and we're able to extract the timestamp if we want to see how long it was since the last message was received. The configuration, the non-blocking receive is one shot, so once it's done, it's done. So if we want to do it again, we then call receive FIFO non-blocking again to receive the next message through the callback function. So if I set a breakpoint here, we can see it hits, and this should give us the details of the message that was received. And we can see that the length is 64 bytes, and we can see 64 bytes of data from the received message. So Brendan, do you want to take over at this point?
Yeah, just to mention about this slide about where to get more information and so on. So the LPC micros are all fully described on our website, nxp.com. Data sheets, user manuals and so on are all freely available. The demo board Andy's been using today has an order code of OM13094. So following that URL, you can go to that page, you can get the drivers that Andy's been using, an example code that's all under the downloads tab, and you can also get the MCU Expresso tools following this link, so that gives you access to our IDE that Andy was also using today, and the SDK. The SDK includes a CAN driver. The CAN FD driver that Andy's been showing is again available under that Downloads tab and is completely compatible with the MCU Espresso SDK. So all of the information is there. The board's available either through our distributors, or you can directly buy it with a credit card if you want to do that. So I think back to you there, Andy, for your wrap up on ESA before we take it to questions.
So that is the end of this presentation, and I hope you found it informative and interesting, and learned some new things about CAN FD and see ways that it could be incorporated into your future developments and products.
Okay, thank you, Andy. I think that was great. So we do have a few questions. Quite a lot of them are fairly specific to people's individual needs, but I'll try and just recap some of those. So we did have a couple of people asking about opinions on the deployment of CAN FD into the market, Andy, and you've highlighted some reasons why it would be deployed. And I think, you know, from the NXP side, we certainly in our automotive colleagues side, we know that the automotive manufacturers are all looking at CAN FD because of the obvious benefits that you highlighted. Do you have any kind of views or opinions on how from your consultancy work, how quickly it seems to be ramping up in the market?
Yeah, I mean, we have a constant demand for customers that need more bandwidth, and there are some applications that we've seen where customers are pushing the limits of classical CAN. They want to run 1 megabit per second, and they want to do it near to 100% bus load, which is not recommended. And those kinds of customers, they're really keen on looking at CAN FD to give them the extra headroom that they need for their projects, so they can get more data sent over. In particular, bootloading is one area that people are a lot interested in because bootloading will be able to take place a lot faster.
And there's some more security benefits that come with that too, correct?
Yeah, definitely. I mean, the extra data space in the messages means you can add in additional encryption settings. You can have additional protocol for encryption before and after transfers. So yes, there's a lot more you can do on the security side when it comes to CAN FD.
So there was one question which is more specific to the hardware, which is asking about looking at power consumption between CAN and CAN FD mode. Well, we do have obviously data in our data sheets about power consumption, but the board has a built-in power measurement capability. So using that evaluation board, you can go to between CAN and CAN FD mode and do your own power measurements. But the main power differences are going to really come from the higher transmission rates, because basically the transmit path is the same kind of drivers, and the networking characteristics are very similar. So it's going to be additional switching which will make difference. So CAN FD is going to be more power hungry if you use it in its capabilities, to its fullest capabilities, just by the nature of that higher data rate. So to answer that question. Okay, so I think that was basically the questions that we had. Just one last one just popped in about physical link length, so cable lengths and so on. Do you have any comments generically you make on that, Andy? I think because the characteristics are the same. It has basically the same kind of capabilities as CAN, or you do need superior cabling obviously to get to really higher rates, correct?
Yeah, I mean the faster you go, the more critical the specific topology is going to become. You might have to use shorter drop lengths and shorter overall network length, but that's just a general because you're going faster and reflectance.
Okay. All right, so I think we covered the generally applicable questions here. For people who have other questions, feel free to post on our community. That's community.nxp.com, and as Andy mentioned, we do contract with ESA to have them to respond to questions. They actually put together a very nice FAQ for us about CAN bus, so you'll see them popping up on our community from time to time helping with the questions. So please do ask, get involved. So we'll wrap it up here. The presentation will be posted on our website. That takes a few days to come through. You will get an email when that's available. We will have the recording of the webinar available initially on the GoToMeeting server, and again you'll be able to access that, and we will then move it on to the NXP servers later. This is part one of a two-part series, so Andy's colleague Olaf is going to be presenting at the end of June, and then he's going to be looking at the CAN-FD bootloaders and more specific items around that and those capabilities. There is just one last question I did forget I was going to ask you about, Andy. A few people asking about CAN Open support and wondering if you have any gut feel for when the standards committee might converge on something, so we'd start to see a broadly accepted specification becoming available. I know it's not one you control, but I wonder if you have an opinion on that.
I would say right now it's probably 70% there, maybe even 80% there. There is the bulk of the changes to the SDO protocol, because there's much more flexibility allowed now than before. And the core of that has been specified, and several companies, us included, have an implementation that's working. It's just there is a few aspects to do with that that still need to be sorted out. I would hope later on this year it gets finalized, and I think that would be version 5 of the CAN Open standard when it's released.
Okay, well, thank you very much, Andy. I think we're going to wrap it up there. Like I said, join us again in about a month's time, where you're going to get another great in-depth, detailed webinar about CAN-FD, and I think you'll see how great the ESA team is at CAN and CAN-FD bus, and their expertise is one we value a lot in our partner program. So thanks everyone for joining us. We really appreciate your time, and we'll see you at the next webinar. Thank you.